Alright, let's work on some examples. Suppose we have a tube and we have some air that's pushing a ball around this tube, so it's traveling in a circle. And let's say it has a little window, and we look in and notice that the ball is moving at 10 meters per second. We can also observe that it passes the window once per 2 seconds, or every 2 seconds. Every 2 seconds, or once per 2 seconds, means that it makes one revolution So 1 revolution per 2 seconds. And a revolution is the same thing as a cycle, so that's 1 cycle per 2 seconds, or 0.5 cycles per second. And the question is, what is the diameter of this tube? I'll call it D. Well, we know that the tangential velocity is equal to the radius times omega in radians per second. So here is the radius. This would be the tangential speed. And we're trying to solve for diameter. What is the diameter? Well, we know that omega in radians is just equal to 2 pi times omega in cycles per second. And we know that radius is just half the diameter. So we can replace the radius with d over 2. And we can replace omega in radians per second with 2 pi times omega cycles. The 2's cancel out, giving us the equation that the tangential speed is equal to the diameter times pi times omega in cycles per second. Doing some algebra, we can solve for the diameter. The diameter would thus be equal to the tangential speed over pi times omega cycles. This would be equal to 10 meters per second divided by pi times, and our omegas in cycles per second is 0.5. The per second cancel each other out. Cycles is a fictitious unit. It doesn't represent any real quantity, which gives us just meters. So 10 divided by half is 20. 20 divided by 3.1415. That's about 3.1831 meters. So the diameter of 2 is a little over 3 meters. Let's do another problem. So let's do another example. Let's estimate the distance to the moon. Trying to find some more precise values. Getting hard. Not do that example. I'm getting 3 times off by using this approximate. I was supposed to say we could estimate the distance to the moon based off of the speed, but just doing the trivial math on some really bad estimates for speed, I don't get anywhere near the correct answer because it's not moving in a perfect circle. It's moving in an elliptical orbit. Also, the Earth is rotating around it too. Yeah, never mind. I was going to try doing. We have Earth. We have the Moon. And technically, the Moon is orbiting around the center of gravity. It's not moving. It's not orbiting around the center of point. So it's not doing it. So scratch that problem. Let's do some more different ones. Here's one. Let's suppose we have a roller coaster or a racetrack. So we have a racetrack that has a loop-de-loop. So how fast do we have to have a car go in order for it to go around this loop? And let's make this loop, let's make it big. Let's make it 1 meter. So how fast does this car need to go in order to go around a circle? So let's look at what happens when the car is at the very top. So when the car is at the very top. And let's look at it in a rotating frame of reference. So let's put ourselves inside the car. It's going to experience two forces. It's going to experience a gravitational force that would be equal to the mass times the acceleration of gravity. And let's make this a 0.5 kilogram car. And it will also experience a centrifugal force. Again, it's a fictitious force, but if we're inside the car, it's real. Our feel is real. And what we want it to do is we want FC to be at least, it needs to be greater than or equal to m times g. So we either need FC to cancel it out, or we need it to at least be pushing against the track. So the centrifugal force must be the minimum value. So we want FC greater than or equal to mass times g, the gravitational force. Let me actually write that. So you want the centrifugal force to be greater than or equal to the gravitational force. Centrifugal force is equal to mass times the velocity squared over the radius, and it has to be greater than or equal to m times g. First thing, as I've taught, if you have the same variable being multiplied on both sides, you can divide by that variable to get rid of it. So dividing by m cancels out the mass on both sides. So the mass is irrelevant. That's because everything accelerates down at the same rate, regardless of mass. At least if it's due to gravity. So that means that velocity squared over r has to be greater than or equal to g. And if we multiply r to both sides, assuming that r is positive, we can keep this greater than or equal to r times g. If r was negative, note that we would have to flip the sign. But since distance is always positive, we can keep it greater than or equal to. Then we can take the square root. And again, it's plus or minus. And we would have to do the sign, but we're only looking for speed and not really velocity, so we can ignore direction. And so that the speed required must be greater than or equal to square root of 1 meter times 9.8 meters per second squared. Yes. All right. I got a question. What do you do? All right. So that is equal to meter squared divided by second squared to the square root gives us meters per second. So you have to be going at least 3.1321 meters per second. Note though, in real life, we would also have to account for friction, and that would be another force adding to this equation. So if you were to attempt this, note that this is just barely enough to make it stay on the track. In real life, friction would most definitely be enough to make this go off. But you can get a rough estimate, ignoring friction, and then you just know that you need to be slightly higher than this value to ensure that it stays on the track. See if I can come up with another data. Alright. Suppose we had some mass going around a 2-meter loop, and let's say that the speed here is 5 meters per second, tangential speed. And let's say that the force is 500 newtons. What would be the mass of the object? So tangential velocity is equal to centrifugal force equal to mass times velocity squared over r. Solving for mass, we're being multiplied by the fraction dt squared over r, so we multiply by the reciprocal. So force times r over dt squared is our mass. So the mass would be equal to the force, 500 newtons, times 2 meters, divided by tangential speed squared, so 5 meters per second squared. So that'd be 1,000 divided by 25, which is 40 kilograms. So the object would have a mass of 40 kilograms. Alright, I think that's enough. So my plan is Monday, I'm going to review for the test and upload a video. Tuesday, I'm going to give out the test. It will be on Google Classroom. It'll be multiple choice. And also, Kobe, you need to be turning in your homework and watching these videos.